Okay, we have just seen that our three variable we have just seen that our three variables such as LR, GDP and money supply, they are co-integrated. So we can run the error correction model. And error correction model actually is a single equation model. Right, that we shall be developing now. And here LR should be the dependent variable and GDP and money supply would be the independent variables. So we can develop the model now. So I go to statistics as before, right? So I make it clear. Okay, I make it clear. Then I do the statistics. Okay, multivariate times. I choose the multivariate. Then I choose the vector error correction model, right? I choose it. Okay, and here we have one co-integrating equation that we have seen already, and maximum lag I put 3, and because lag selection criteria has advised me to take maximum lag 3, and dependent variable I put LR first. I put LR first intentionally, then I put GDP, then I put M. So that is my model, right? And LR is the dependent variable, and this one actually our error correction model, right? And here I take the constant, then time settings I put it observation as before, then I select yearly as before, then click OK. Okay, then what else? Anything from reporting? No, nothing from reporting. So here I put LR first intentionally, because this one would be our error correction model where LR is the dependent variable. Okay, everything is set, so I proceed. Okay, this is the outcome. Okay, this is the outcome has come up. Okay, so here actually there are actually the model here. This is dependent variable DLR, right? And also there is one more dependent variable, and also there is one more dependent variable, right? But here what I shall do, I shall choose the first one, and because that is our target model, and I put LR first. So this one actually is our target model where lending rate or LR is the dependent variable. Okay, and this one actually error correction model, and only this one I shall be picking up. Only this one I shall be taking from this model. Okay, and here you can see this is dependent variable. Okay, and what happens? So here the software that we are using normally automatically convert all the variables into first difference. Okay, I say suppose I last time I put LR has become DLR because they have automatically converted to first difference, and the first difference data is stationary that we have already assumed, and here we need the stationary data in the error correction model, right? And also not only this one, all the variables have been converted to first difference. All the variables, not only this one, all the variables. Okay, and here this is dependent variable DLR, and all these are independent variables from here, right? Independent variables are here. Okay. Okay, first I talk about coefficient, standard error, and Z value. Okay, what is this one? Co-integrating equation 1. And last time we had one co-integrating equation. So we can call this one error correction term, right? Okay. And this one is the standard error, and this one is the Z statistics, and this one is the corresponding probability. Okay. Here the Z value minus 6.08. How? Coefficient minus 1.466 divided by 0.24, I can get minus 6.08. Also here, that means coefficient divided by standard error, you can get the Z statistics all the time. Suppose this divided by this, you can get 2.85 all the time, and that is Z statistics. Okay, here you can see what is this variable? This is the lag 1 of LR. What is this variable? Lag 2 of LR. What about this one? Lag 1 of M. What is M? Money supply. And this one lag 2 of M. Okay. And here I can see the error correction term is negative, right? And also it is significant because the p-value is very small, right? Meaning that this co-integrating equation 1, this error term is significant. Okay, what does mean by this minus minus sorry, what does mean by this? Okay, this one actually called speed of adjustment. Speed of adjustment towards equilibrium, right? So that is actually error correction term. Error correction term, and we can say that we can say that that it is adjusting very fast, right, at the rate of 146%, right? It is adjusting at the rate of 146% towards long run equilibrium, right? So it is adjusting this one is 146%. It is adjusting very fast at the rate of 146% towards long run equilibrium. That means this error correction model is adjusting very fast at the rate of 146% towards long run equilibrium, but make sure the coefficient sign must be negative and it must be significant. Only then it can adjust towards long run equilibrium, right? So the sign should be negative and it should be significant. Okay, so this part is done, and the second part we can talk about short run adjustment. So actually all these coefficients are short run coefficient. These coefficients are short run, right? Sorry, all these coefficients are short run coefficient. Sorry. Okay, first I talk about this coefficient. That means lag 1 of LR, right? Lag 1 of LR. Is it significant? Yes, because p value is 0.4%, which is less than 5%. So meaning that lag 1 of LR is significant to explain our dependent variable, which is LR. So what about the second one, lag 2? It is not significant because p value is very high, 9.6%. But GDP lag 1, yes, it is significant individually to explain our dependent variable. What about this one? It is not significant. What about the lag 1 of money supply? Yes, it is significant individually. And what about lag 2? No, it is not significant individually to explain our dependent variable, which is DLR. Okay. Okay, we can check that jointly whether LD and L2D jointly whether they can cause the LR or not. That means I can call it, I can here use it that short run effect from GDP to LR, right? Okay, so how to check the short run effect? So I go to statistics, then I come here, I go to post estimation, then I go to test, then I go to test linear hypothesis. Okay, then I have to create the specification. I create it, then I put coefficient in specific equation at 0, and I put my dependent variable DLR, and I want to check whether GDP lag 1 and GDP lag 2 whether they are jointly can cause DLR or not, right? Okay, the hypothesis is set, so they are actually I am to check whether these two independent variables are 0 or not. Okay, it is set, then I press OK, then OK. So here you can see the hypothesis it is 0 or 0, right? And it is chi-square, and it is the probability. So here we can see that we can reject the null hypothesis, meaning that they are not 0, because it is our null hypothesis, right? They are not 0, meaning that meaning that LD and L2D are not 0, meaning that GDP can cause LR, right? GDP can cause LR, but make sure these are short run effect, right? Short run effect, because all these coefficients are short run coefficient. Okay, then I talk about this one, whether money supply, that is M, can cause LR or not in the short run, right? Okay, as before, I check whether LD and L2D they are 0 or not. So I proceed as before. So post estimation, I go to test linear hypothesis, then I choose the reset our specification, create. As before, I choose this one, and equation is DLR, and this time we want to check whether money supply, right? That means lag 1 of money supply, lag 2 of money supply, they are equal to 0 or not, right? Okay, I press OK. I press OK. Okay, here you can see, so that is the null hypothesis, chi-square value, corresponding probability. The probability value is 11.86, meaning that it is more than 5%. So we cannot reject null hypothesis. Rather, we accept null hypothesis, meaning that they are 0. LD, these two variables are 0, meaning that I come back to my model, that is my model, right? Meaning that the M, which is money supply, meaning that LD and L2D are 0, meaning that money supply cannot cause LR in the short run, right? Okay. So that is the decision of this error correction model, right? And from here, actually I shall be choosing only this model, right? Only this model. Okay. Okay, now I can check as a whole, the whole system model, right? The whole system model, because this one actually the part of the whole system model, we can check the whole system model also, right? We can also check the whole system model that whether the whole system model has serial correlation or not. That we can also check. Okay. So I go to statistics, then I go to as before multivariate time series, then I go to VECM diagnostic and test, then I can go to LM test for residual autocorrelation, then here I take 2, right? Click on it. It's coming up. Okay, here is the Lagrange multiplier test, lag 1, lag 2, right? And the null hypothesis is there is no autocorrelation at lag order, right? But here at lag 1, the p-value is 34.56%, meaning that I cannot reject null hypothesis. That is, there is no autocorrelation. And also lag 2, I cannot reject null hypothesis because p-value is 10.15%. So meaning that in the whole system model there is no autocorrelation, meaning that there is no serial correlation. So we are happy about the whole system model. Okay, then we can check also one more thing, whether the residuals are normally distributed or not. I go to statistics as before, multivariate time series, and vector error correction diagnostic and test for normally distributed disturbances. I click here, and here I choose the Jarkabera statistics only. Okay, so here you can see, okay, we have 3 models, right? One is DLR, DGDP and DM, and here DLR actually our target model, and here the probability is 71.64%, the p-value. And what is our null hypothesis? The null hypothesis is the residuals are normally distributed, and that is desirable. And here the p-value is more than 5%, right? So we cannot reject null hypothesis. Rather, we accept null hypothesis, meaning that for our model, which is DLR, the residuals are normally distributed. So we are happy about it because that is desirable. But when I consider all, that means the whole system, right? Then I see that p-value is less than 5%, meaning that the residual is not normally distributed, and that is not desirable. But actually we are talking about DLR, that is our target model, and here the residuals are normally distributed, so we can accept the result somehow, right? Although as a whole residuals are not normally distributed. Okay, for this model, what is the problem? For this model, in the whole system model, there is serial correlation, so that is not desirable. And but one thing is good, our error correction model, which is DLR, the residuals are normally distributed, so we are happy about it. So thank you very much for being with me for a while.